vibration measurement devices. So first of all, we studied about transducers and vibration pickup. After that, we studied the velocity like velometer, vibrometer, and accelerometer. Basically, their working principle, and like how can we measure the actual response of the system using these instruments. So, and at the end, we studied about phase distortion and frequency measurement. So now there are some. I'll be solving the previous year assignment. So some of the questions are basically theoretical and they are fill in the blank type. So I think I'll touch them at the end. So we will start by solving certain numericals. Okay, this is also part of the previous year assignment itself. So let's start then. So the first question is, I hope my screen is visible. So it is that a vibrometer having an amplitude of vibration of machine part as 4 mm and zeta equal to 0 point, performs harmonic motion. Okay. If the difference between the maximum and minimum recorded values of amplitude is 10 mm, determine the natural frequency of vibrometer if the frequency of machine part, okay, basically the vibration part, is 12 radians per second. So basically what does the first question say? It says that we have a vibrating machine and on that we have mounted a vibrometer, okay, and the vibrometer is also performing a harmonic motion, and yeah, and the amplitude and zeta of the vibrometer are given, okay, and then we have been said about the difference between the maximum amplitude, the recorded value of amplitude is 10 mm, okay. So basically what the question is trying to say is that, yeah, so the question is telling that for this system, okay, we know that this is how we mount a vibrometer, okay, it is K, it is damper, and here we have X, I hope it is visible, and this is the vibrating machine, okay, it has a motion Y, okay. Now the question tells us that for this Y it has been given that its amplitude is, that is Y sine say omega t. Now this capital Y is 4 mm and also the zeta has been given as 0.2, right? Now difference between the maximum and minimum recorded values of amplitude is 10 mm. So what is this amplitude? We know that whatever we record from the vibrometer or any vibration pickup, it is basically the relative terms. Obviously, we are using them for that purpose only, because they are vibration measurement instruments. So basically, they measure the relative part. So here also, if the mass is having an absolute motion of x, so the relative motion between the mass and the basically the relative motion between the vibrometer and the vibrating machine is x minus y, right? So now it's telling that it's the difference between the maximum and minimum recorded value. So it's telling that z max minus z minimum is equal to 10. Okay. Now since it's performing a harmonic motion, we know that the z max and z minimum, they will be magnitude wise, they will be same. Just there will be sign difference. So basically, z is equal to what? 10 upon 2. Okay, it will be 2z. When we add that, we can put z max equal to z min equal to z. So it will be 2z is equal to 10. Sorry, here you write it like this, and which will imply that z is equal to 10. Okay. Now we have z now, and we have y. Y has already been given as 4 mm. Now we have zeta, and also the the frequency of the machine part is given. So it's simple. We know the formula for the response of this system. Okay, it's similar as and how we found out the response of the excitation of base. Okay, so here we can put it like this. Okay, you know the formula, z upon y is equal to r square upon under root of 1 minus r square whole square plus 2 zeta r square, right? No, I think it's whole square, yeah. 2 zeta r whole square. Now it will be 5 by 4, okay, is equal to r square upon under root of 1 minus r square whole square and plus 2 zeta r whole square. Now I think we can put the value of r later, like, because r is omega upon omega n, so omega n we have to find. Okay, omega is given, it's at 12 radians, so we'll put it at n. First we'll try to simplify this equation. Okay, so by squaring on both sides, it will be r4 1 minus r square whole square plus 2 zeta is 0.2, so I am putting it, okay, r square. Now from here you can see it will be 25 by 16 is equal to r to the power 4 upon 1 minus r square whole square will be 1 plus r to the power 4 minus 2 r square. Okay, yeah, and it will be plus 0.4 r square. 0.4 will also be squared, so let me write it here only. So 0.4 squared will be wait a minute. Okay, I can write it like this only. Okay, now we can multiply, cross multiply, so it will be 25 into 1 plus r to the power 4 minus 2 r square plus 25 into 0.4 square into r square is equal to 16 r to the power 4. So it will be 25 plus 25 r to the power 4 minus 50 r square, right, plus this simplified will be 4 r square minus 16 r to the power 4 is equal to 0. Now it will be 9 r to the power 4 minus, it will be 50 minus 4 is 46 r square and plus 25 equal to 0. Now okay, we can write it as 9t square. Okay, put r square is equal to t, so minus 46t plus 25. Now it is a quadratic, you can simply solve it, or you can solve it in calculator as well. So I have already done it. So here when we find the roots, T1 is equal to, comes out to be 4.492 and T2 comes out to be 0.61827. Okay, from here when we take the root, it will be R1 is equal to 2.119. Okay, we don't take the negative values, and R2 will be basically 0.789. Okay, now omega n is equal to, we know that R is equal to basically omega upon omega n, right? You know this formula, it's omega upon omega n, which will imply that R into omega, okay, omega n we have to find, right? So omega n will be omega upon R. Now omega is given as 12, now R. Now here, which one R should we consider? If you have gone through the lectures, we know that in case of vibrometer, basically our Z by Y, okay, this is our response which I basically wrote here. We want its value to come out as 1. Why do we want so? Actually, we are not interested in the relative amplitude, right? We use any vibration measurement device so that we can know about the response of our machine or any instrument which we are using. In this case, it's a vibration part. So here we basically want to know the response or amplitude of the vibration machine, that is Y. So we are not interested in Z. So basically but however we cannot measure Y or we cannot measure X, we can only measure the relative amplitude between them, that is Z. So we want Z be close to Y, okay, so that's why we want that Z by Y should be, I will not say equal, but approximately equal to 1. And for this condition, when you put this condition here, you find out that for this condition to be true, R should be greater than 3, right? Now here also R should be greater or equal to 3. So in this case, basically none of the values is coming out to be greater than 3, right? But if you remember the frequency graphs, okay, the basically frequency ratio, okay, say this is frequency ratio and this is Z upon Y, right? And here this is 1, then this is 2 and this is 0. So the frequency ratio will be something like this, okay, the graph is coming out to be something like this. For different values of damping. So you will see that I have not made it to this scale, okay, you can write it like this. What you see is that as we increase the value of frequency ratio or simply R, okay, this Z by Y tends to 1, okay, here it is 1. So at 3 exactly it is like equal to 1. So basically we will not choose any value of R less than this. We will choose it above this because you know that this region, it is suitable for range of accelerometer, okay, and this is more suitable for the higher the value for, it is more suitable for vibrometers. So here in our case, we will therefore choose this value, okay. So now when I put this value here, okay, if you use your calculator, you can see that this is coming out to be 5.66. Okay, so that is our required answer. Let me check the graphs once, okay, if I have done them correctly or not. the graphs you can see here also. Okay, see at 3 they will be equal to 1, but here after 2 also they approach this range only. So we will choose a value of r closer to this, not below this. Okay, so that's why we discard that value and we choose this value. Okay. So I hope you have understood this question. Now okay, so the next question is, okay, yeah. So what is sorry, what is the relative displacement of the end of the cantilever reed with respect to base for the system shown below. So we have a reed, you know that it's used for frequency measurements. So this will be something like this, as a scale, and it's mounted here. It has just a spring. Okay, so damper is not given in this case. Obviously. Yeah. So this is a cantilever reed and it's asking the relative displacement of the end of this cantilever beam with respect to the base of the system. Now, what is the information that is given in the question? That the base is performing a harmonic motion, okay? Performing a harmonic motion. Let me write it like this. Y is equal to 0.8 sine 10 t centimeter. Okay, so the amplitude is given in centimeters in a direction perpendicular to the reed. Perpendicular to reed. Okay. Now the natural frequency of the system is twice the disturbing frequency. So basically omega n is equal to twice omega. Omega is the disturbing frequency and omega n is the natural frequency of the system. So this is the information that has been given to us. Now from here, again we know that we can calculate z upon y for the system. Okay, the formula, we have the formula z upon y is equal to r square upon under root of 1 minus r square whole square plus 2 zeta r. Now what we need to find, zeta is not there because there is no damping. Okay, so it will be r square upon 1 minus r square, and r we can find from here. Okay, it's very simple. R is given from this statement, so omega upon omega n is equal to r. So omega upon omega n is 1 by 2. Right. Now z upon y will be equal to r square upon 1 minus r square. Okay, I have simplified the formula. So it will be z, z is capital Y into r square upon 1 minus r square, which is equal to 0.8 into 0.5 square upon 1 minus 0.5 square. Now this calculation is very simple, so it will come out to be 0.8 into 0.33. You can check it for yourself. So it will be 2.66 centimeter. Okay. So this is basically the displacement of the end of cantilever reed with respect to the base. So basically the relative. Okay. You can solve another problem. Okay. Now the question says, what will be the maximum percent error of an accelerometer in the frequency ratio range. Sorry, I don't know why is this happening. In the frequency ratio range zero to 0.5. Okay, we know that we operate accelerometer in this range with a damping ratio 0, with zeta equal to 0. Now it's asking about the maximum percent error. Okay, so basically the error function here. Okay, so basically this is called error factor. So it is equal to r square upon under root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so this is the error factor, and since zeta has been given as 0, this term will vanish and e will be equal to r square upon 1 minus r square. Okay, now if we put the value of r equal to 0, okay, we know that it will come out to be obviously 0. So we have to make the error maximum. So we will put r equal to 0.5. Okay. Now it will come out to be 0.33. So the error we have is equal to 33%. Okay. This question was very straightforward. So we will move to the next question. So see, a vibration measuring device is used to find the acceleration of a machine running at 125 rpm. If the natural frequency of the instrument is 6 Hz and it shows 0.005 centimeter of amplitude, the acceleration reading is. Okay. So we have been given a vibration measuring device and we have been given a machine. We know the operating speed of the machine. So basically we know the omega n of the, basically we know the omega for the vibration pickup or for the vibration measuring device. We know the omega and we know its omega n also. Okay. Now what we have to find? Basically we have to find the relative acceleration, that is z dot, the relative part of it. Okay. Z double dot, sorry. Now see, I'll write the question first for your reference. Okay. So a vibration measuring device is used to find the acceleration of a machine running at 125 rpm. Okay, if the natural frequency of the instrument, okay, basically the vibration measuring instrument, is 6 hertz and it shows amplitude of 0.005 centimeter, find acceleration. Okay. So as I said that first let's calculate omega. We know that omega is equal to 2 pi n upon 60. So here 2 pi n is given as 125 radian per minute. So I am converting it to second. That's why I divided by 60. So when you calculate this, okay, or let me keep it like it will be 25 by 6, I guess. Yeah, 25 by 6 pi. Okay. Now omega n is what? Omega n is 2 pi f. So 2 pi frequency is given as 6 hertz. Okay. So it will be 2 pi into 6, so it will be 12 pi. Now from here the value of r is omega upon omega n, right? So it will be 25 pi by 6 into 12 pi. Okay. Now if you calculate it, okay, I have recalculated it. So it is coming out to be 0.347. Okay. So now this is the value of r. Now the value of z has been given, okay, and zeta has not been provided, or zeta is considered here the 0 then. Okay, so z by y is equal to r square upon 1 minus r square. Okay, so it will be equal to z by y 0.347 squared upon 1 minus 0.347 squared. Now if you evaluate this expression, it is coming out to be 0.137, right? Now from here y is equal to what? Z upon 0.137, so it is equal to 0.005 upon 0.137, and it is equal to 0.0364. Okay, so basically this is the y. Now if we have to calculate acceleration, okay, so acceleration we know that, yeah, acceleration will be magnitude of this will be omega square into y. So omega square is here what? We have already calculated omega square, that is 25 by 6 pi. Okay, 25 by 6 pi square into y is 0.0364. Right. Now this will be 13.09 squared into 0.0364. You can use your calculators to cross check the answer maybe once. I have already calculated it on my sheet. So yeah, it is coming out to be 6.237. Okay. So basically this is, I hope when you solve it you are also getting the same answer. Okay, so moving to the next question. A seismic instrument with a natural frequency of 6 Hz is used to measure the vibration of a machine operating at 120 RPM. The relative displacement is given. Determine the amplitude of vibration of machine, neglect damping. Okay, so it's basically similar to the previous question. Okay, in the previous question we had to find acceleration. Here we have to only find the magnitude of amplitude of vibration. Okay, so yeah, a seismic instrument, basically a vibration pickup, with a natural frequency of 6 Hz is used to measure the vibration of a machine operating at 120 RPM. Okay, the relative displacement of seismic mass as read from instrument is 0.05 mm. Okay, similar to previous question. Determine the amplitude of vibration of machine and neglect damping. So basically again omega has been given, okay, and after that RPM has been given, so we can find the omega, and okay, the operating speed has been given, so we can find the omega, and from these two things we will get the R, and from R we can calculate Z upon Y. Z is already given, so that is how we'll find Y. Okay, so very straightforward question. I think it should not take you like much time to solve. So omega is equal to 2 pi f, so it will be 2 into pi into 6, right? So it will be 12 pi. Then omega n is 120 RPM, which is equal to 2 pi into 120 n upon 60. Okay, 2 pi n upon 60. So it's simple, 4 pi. Right. Now from here we can calculate R, which is omega by omega n. So omega is 12 pi and this is 4 pi, so it will be simply 3. So our value is large here. Now since zeta is 0, okay, you know that Z upon Y is what? R square upon under root of 1 minus R square whole square plus 2 zeta R whole square. Now this term is 0, so it becomes R square upon 1 minus R square. That is why I am simply writing R square upon 1 minus R square, because we do not like need to repeat writing this big expression. Okay, when zeta is equal to 0, we will simply write R square upon 1 minus R square. Now yeah, here we can put the value of R and we can put the value of Z also. So let us see, Y is equal to 1 upon Z into R square upon 1 minus R square. So 1 upon Z is equal to 0.05 mm, right? And R square will be 4. R is 4, right? Oh, sorry. 4, 3 are 12, right? So it will be 3. Yeah. Or maybe this is 3 pi. No, okay. So on my notes I have made mistake. I have put R as 3. So sorry, R as 4. So anyways we can do it now. It's 3 square upon 1 minus 3 square. So it will be 1 upon 0 0.05. So it will be 9 upon. Now here you know that basically we take the modulus of 1 minus r square, because since uh, it is whole squared always here, so it will always open with a mod. So if it is a negative value, it will open with a negative sign. If it's a positive value, it will open with a positive sign. So since it will come out to be a negative value, we will write it as r square minus 1. Okay, so that will be 9 minus 1, which is 8. So basically let me just calculate it using calculator. 9 yeah, so it is coming out to be 22.5 mm. Okay, I guess that is correct. Let me check it once, because I'm not getting sure if it's correct or not. I'm very omega upon omega n. 60 into 2 to the 4 pi. This is correct. Okay. Now here it's 12 pi radians per second. Okay, so yeah, the correction, this is correct. Now we can maybe move to the next question. Okay. So the question is, okay, so a spring mass system having a static deflection of 10 mm and negligible damping is used as a vibrometer. When mounted on a machine operated at 4000 rpm, the relative amplitude is recorded as 1 mm. Find the maximum values of velocity of the machine. Okay, so we have been given a spring mass system which has a static deflection of 10 mm. So basically we can find out omega n from here, right? You know omega n is under root of g upon static deflection. Okay, so from here we'll find omega n. Now omega is given because 4000 rpm we can easily convert it to radian per second. Okay, so now we have omega, now we have omega n, we can calculate r. Then relative amplitude, that is z is equal to 1, so we can put it in the formula. So this question is basically straightforward, and after finding the value, we can multiply it with omega to convert it to velocity, right? So let's start doing it. Okay, give me a minute. here we made a little mistake. Okay, it will be, let me erase it. So here y will be z into 1 minus r square upon r square, right? It will be 0.05 mm, which is given in the question, into 1 minus r is 3 square. Okay, basically we can write 3 square minus 1, so which is 8 by 9. Okay, so it's we can simply calculate it. It will come out to be 0.044 mm. Okay, in centimeters it will be 0.004 centimeter. Okay, so yes, sorry, it will be multiplied with 10. It will be 0.4 mm centimeter. Sorry. Um, Now let me write the question I just mentioned here. A seismic instrument with a natural frequency of 6 Hz is used to measure the vibration of a machine. Operating at seismic instrument. Sorry, this is not the question. Let me raise it. So the question is a spring a spring mass system having a static deflection ten mm and negligible damping, that is zeta is equal to 0, used as a vibrometer. When mounted on a machine operating at 4000 rpm, the relative amplitude is recorded as 1 mm. Find the maximum value of velocity. Of machine. Okay, I've explained the question. So I'll quickly go through the solution as well. So XST is given as 10 mm, right? Static deflection, or you can simply write it as delta ST, whatever you like. So I'm going through the notations. Now omega n is equal to under root of g by delta ST. So it will be under root of 9.8 upon 10 into 10 to the power minus 3. Here you'll convert it to meters so that you get answer in radians. Okay. Just the SI conversion. Now omega n we have. Now omega we already know. It is equal to what? 2 pi f. 2 pi n upon 60. So it will be 2 pi n is 2000 upon 60. Now I have this. Okay, let's just simplify it like this. Okay, now R value is equal to what? Omega upon omega n. So omega will be 400 pi by 3 and omega n is 31.32. Now when you evaluate this, okay, you can check once, but I have calculated it, so it is 13.37. Okay. Now we have R, zeta is 0, so we can simply write Z upon Y is equal to R square upon 1 minus R square, which implies that Y is equal to Z is 1 mm, okay, into 1 minus R square upon R square. So it will be 1 into 1 minus, okay, basically R square minus 1. Okay, you now know the logic how you have to open it every time. So it will be R square minus 1 upon R. So here also it will be 13.37 square minus 1 upon 13.37 square. Right. Now when you evaluate this, the value of Y comes out to be 0.994. Okay. Now that has not been asked in the question. In question we have been asked about the Vmax. So from the expression of velocity, we know that Vmax it will be what? We know that if Y is Y sine omega t, then when we take Y dot, it will be Y omega sine omega cos omega t. So the maximum will be omega into Y. So omega here it is 400 pi by 3, okay, and 0.994 is our Y. So when you calculate this, it will come out to be 406.53. But this is in mm per second, okay, because I have taken here 1 mm, okay. I have not changed it already. So if you want to convert it to meter per second or centimeter per second, you can simply write it as 41.65 centimeter per second. Okay, so that will be our desired answer. Now going to the next question. So next question we have like a vibrometer having a natural frequency hertz and zeta equal to 0.2 is attached to a structure that performs a harmonic motion the amplitude of recorded values. So recorded values means Z, not Y. Okay, the amplitude of recorded values is 7 mm. Find the amplitude of vibrating structure. That is why we have to find the amplitude of vibrating structure when its frequency is 50 radian per second. So basically omega has been given, okay, omega n has been given and zeta has been given, so all we have to find is y. So here omega n natural frequency is 1 hertz, which is equal to 2 pi, okay. Then omega is equal to 50 radians per second, and the amplitude of recorded values, that is Z, is equal to 7 mm, okay. And zeta is equal to 0.2. So we have that Z upon Y is equal to R square upon under root of 1 minus R square whole square plus 2 zeta R whole square. So basically the concept is same in every question. The wording might be different, but almost it's similar. So let me find R here. So R is omega upon omega n, okay. So that is 50 upon 2 pi, and if you evaluate this thing, it comes out to be, I have done it already, you can confirm, you can cross check. So it is coming out to be 7.95. So 7 mm upon y is equal to 7.95 squared upon under root of 1 minus 7.95 squared whole square plus 2 into 0.2 into 7.95 square, right? So this is coming out to be 7 mm, or let me transfer y here. So y is equal to Z upon, if you calculate this whole thing, okay, it is coming out to be 1.0160, okay. And Z, okay, let me put Z here. So now this is what you get. So Z is 7 mm upon 1.0160, okay. So it is coming out to be 6.88 mm. So that is the amplitude of the vibrating structure, okay. Now maybe we can do 1 or 2 more questions, so and we will wind up this topic. Okay, so look here, a 3 kg mass is suspended in a box by a spring as shown in figure. The box is put on platform. The box is put on platform having vibration y is equal to sine 60 centimeter, given K is equal to 6000 Newton per meter. Okay, the stiffness of the spring has been given. Then the absolute amplitude of the mass. So basically, we don't have to find Z, we have to find X. Okay, that is the absolute amplitude of the mass. Okay, will be. So let me quickly draw this figure. Okay, in this figure we have this vibrating structure. Okay, this is the vibrating structure. And then we have a spring and mass, okay, attached to this frame, right? And this is Y, and here we can see this mass has X sort of response or motion. So basically here we don't have a damper, so obviously it will become relatively easy. Now first of all, we will find the natural frequency for this spring mass system. So omega n would be nothing but root of k by m, so which is under root of 6000 by 3, which is root 2000. Okay, so it's 10 root 2, but okay, when you calculate it, it will come out to be 44.121. So this is our omega n. Now basically we know about the response x by y in case when we have base excitation. Okay, so in that case the formula what we get, let me write it down as the first whole formula. Okay, it is 1 under root of 1 plus 2 zeta r square upon 1 minus r square whole square plus 2 zeta r square whole square. So you will not use that formula r square upon this because that has been derived for the relative motion z upon y. But remember from the previous lectures and previous discussions that x upon y is something of this form. Okay, when we discuss the magnification factor and etc. So you must have noticed that this form. If you don't remember it, you can go back and check it. So here now this zeta term will become 0 because there is no damper shown here. So x by y will simply be 1 upon 1 minus r square. So now what we have been given is y. So y amplitude is 1, and then see omega is 6 here because it's sine 6 omega t. So let me write it here only that omega is 6 radians per second. Okay, so it will become 1 upon 1 minus r is omega upon omega n, so it will be 6 upon 44.12 whole square. Okay, and if you calculate it, then let me use the calculator. I have not done it. Yeah, so this expression is coming out to be 1.0188. Okay, so it's x by y. Now y is, since y is 1 mm, so it will be 1 into 1.0188. Okay, simply 1.0188. Let me see if it was in mm. No, it's in centimeter. Okay, so here it's in centimeter, so this will also be in centimeters. So this is basically the response, the absolute response of the mass m. And now it's not recording. So let's move to the next question. Okay, so yeah, this will be the last question of the session. Okay, I think in fact this is the last question of the assignment. Then there are a couple of fill in the blanks, as I mentioned at the start of the session. So maybe we would discuss them orally, or let's do this question first. Okay, so a spring mass system with m is equal to 0.8 kg and k equal to 15,000 Newton per mm. Okay, Newton per meter, sorry, with negligible damping. So negligible damping means zeta 0. Okay, it's used as a vibration pickup. Okay, so all these terms you have to catch, they are same. Vibration pickup or maybe a seismic instrument is mentioned. So now it's mounted on a structure with an amplitude of 6 mm. Okay, so when mounted on a structure vibrating with amplitude of 6 mm. Okay, so the vibrating structure has this amplitude, and total displacement of mass of pickup is observed, and total displacement of mass of pickup is observed to be 14 mm. So basically what you see here, if it's mentioned that the total displacement of mass of pickup is given, so that means x has been given, it's not z. Okay, for the mass, the total displacement is 14 mm. Find the frequency in hertz of vibrating structure. Find frequency in hertz of the vibrating structure. So basically omega we have to find, and then we'll multiply it with 2 pi and divide it with 2 pi, then it will be converted to frequency. So basically let me make the information simple for you. Okay, if you are not able to gather it from the question, it's mentioned that our spring mass system has a mass of 0.8 kg and a spring constant is equal to 15,000 Newton per meter. So from here you can in just one step calculate the k by m, that under root k by m, that is the natural frequency. So yeah, it is 15,000 by 0.8, right? So let me write it down like this only for now. Now after that, additional information is that zeta is 0, Y has been given as 6 mm and X has been given as 14 mm. Right. Now, as we know that x by y in case of zeta equal to 0, we just wrote it here, it will be equal to 1 upon 1 minus r square. Now r is basically omega upon omega n, right? So let me first simplify this expression. So we have 14 by 6 is equal to 1 upon 1 minus r squared, okay? So 1 minus r square is 6 by 14, that is say 2 3s are 6, 2 7s are 14. So yeah, 1 minus 3 by 7 is r square. Remember I said that we will always open this 1 minus r square with the modulus, okay, depending because it's always positive. So here I have opened it like 1 minus r square because it will be coming out to be positive. So here it will be 7 minus 3 upon 7, that is 4 by 7 is equal to r squared, right? So it implies omega by omega n is equal to under root of 4 by 7, right, into okay, so yeah, omega n has been already given, so omega is equal to 4 by 7 into under root of 15,000 divided by 0.8. Okay. Now this expression, when you calculate it, it is coming out to be 103.48. Okay. I have already done it for, but you can maybe once check it. Okay. You just don't blindly follow this. So now this is what? 2 pi f, right? So f is equal to 103.48 because we have to give answer in hertz. So it will be divided by 2 pi, and when you evaluate this expression, okay, on your calculator, 16.47 or so. First, I request you all that whenever you're solving these sums, okay, even if you don't understand how to do a question and you're watching this video for reference, you please check the calculations twice, because sometimes I also make calculation mistakes, okay, and it becomes difficult to figure out during the class that where I might have gone wrong. So always double check everything, so that will be helpful. It will also help you in your exams. That will help you, like your speed will increase, and that accuracy also will increase. So yeah, now maybe we can discuss some of the, as I mentioned, there are some one word answers, okay. So the first question is, let me just write it down. Seismic instrument is used in conjunction with another device to measure vibration. It is also known as, okay, so it is basically vibration pickup, right? I think I don't need to write it down. Now after that, which of the following instruments are measure of a frequency of vibrating body? Okay, which of following instruments measure frequency of a vibrating body? Okay, so basically the natural frequency. Yeah, so first is Fullerton tachometer, velometer, then it's tachometer, or both A and B. Okay, so let me write them. Fullerton tachometer, velometer, tachometer. See, we know that velometer is used for measuring the velocity response, right? So for measuring the frequency, we know that we have a Fullerton tachometer. Okay, it's basically a wire of a specific length whose k is continuously changed, because we know that in that case k is equal to 3 ei upon l cube. So the Fullerton tachometer is something like this. Here the length is variable, and here we have our vibrating system of which the frequency we have to measure. So how do we measure this natural frequency? Basically we keep adjusting this L, and we check at which L there was maximum amplitude, because we know that when the amplitude is maximum at the time of resonance, that means when natural frequency of this vibrating system, okay, this vibrating system, when its natural frequency will match this frequency. Okay, so here also see, for this Fullerton tachometer, the omega will be under root of k by m. Now mass is maybe fixed, but this 3ei upon l cube, because we are continuously changing it. Okay, this has a mass at this end, so basically we are continuously changing this omega n. For this omega n, let me write it omega n f. Okay, for Fullerton it will be changing. So when this will become equal to the natural frequency, at that time the amplitude will be very high, other than the other parts. Okay, for other portions it will be normal. So we find out that at this location, yeah, now this is the at this location it made a large amplitude, so it must be the condition of natural frequency, and that means that omega of this vibrating body is matching this, basically the omega of this vibrating body is matching the natural frequency of this. So we can basically equate them, because k is already known to us from this formula, and m is also known to us for this. Okay, so this is basically how it works. You must have gone through this during the lecture also, but anyways it was in the assignment, so I discussed it. Now another question is that which of the following instruments measure displacement of a vibrating body? You know that for displacement we have basically vibrometer, and if we have to measure the for basically displacement, okay, let me write it down. Now for frequency measurement, okay, or let me write it as response or vibration measurement. Basically vibration or response measurement. Okay, so it consists of three things only, because we know that our response is basically say some x. Okay, x as a function of x sine omega t, something like that. So basically what our vibration response is, what we want to get out of the vibration measurement is basically the displacement, or if we differentiate it, it becomes x dot, the velocity, and then the x double dot, which is acceleration. Okay, so displacement, velocity, and acceleration. Okay, so basically these are the three things which ultimately mean that we are measuring the vibration. Now for displacement we use vibrometer. Okay, all these three, let me write them first. Okay, displacement we use vibrometer, for velocity we use velometer. Okay, and for acceleration we use the accelerometer. Okay, now in all the three cases you know that the working principle is almost same. Okay, just the operating range in which the range of R in which we need to operate these, that is different. Okay, and you must have studied the reason for it as well. So basically all these three are seismic instruments, or basically they are called vibration pickups. Okay, they are used in conjunction with this what should I say, transducer, and they are used for the response measurement of the system on which we are working with. So yeah, that's it. Okay, now I think, yeah, there is this, the next question says yeah, the next question was which of the following instruments measure velocity, so that is velometer. Then which of the following instruments measures acceleration, so that is accelerometer. Okay, so I think we have covered pretty much of the this week's content, and I think the new assignment would also be based on a similar pattern as you have seen from the previous assignments as well. So I will stop here now, since the timing of the class was changed because I have to go somewhere uh, to attend a conference like that, and I had to prepone it on a very short notice, so some of you might not have gotten the information. But however, when I'll be back, you can go through this lecture, solve your assignments, and after that, if you have any doubts or queries, you can email me or raise them like on the Neptel platform, or in maybe whenever we will have a chance to meet on the live session again, we can maybe discuss it there. Okay. So thank you very much.